Okay, so hello and welcome back. So this video is a continuation of the previous video where we were talking about basically different types of relations on sets, and the different types of relations that we came up with so far was symmetric, reflexive, and transitive. Was symmetric, reflexive, and transitive. Okay, so in case you're watching this on video, that must most probably appear in the video must appear in a playlist. So I suppose you must have access to the playlist. Otherwise, the playlist is over here. You can search for this name on YouTube, and once you found this playlist, this channel on YouTube, there is a playlist here that I have created. It's called NCERT Mathematics Class 12, Chapter 1, Relations and Functions. And once you go there, you can find all of these videos, related to relations, and so on and so forth. So this is where you can find the rest of these videos in case YouTube doesn't show you the next one or the previous one. Okay, so example number 3 is let L be the set of all lines in a plane. Let L be the set of all lines in a plane. And R be the relation in R, and R be the relation in R defined as R is equal to all the ordered pairs L1, L2, such that L1 is perpendicular to L2. Right? Now you want to show that basically that R is symmetric but neither reflexive nor transitive. Okay. Now the first step always is to understand what the question actually means. Now, based on the concept of a relation, so first of all, L is the set of all lines in a plane, meaning that you can imagine that L is a set that contains all possible lines in one single plane, meaning that you could have basically L1, you have L2, L3, all the way up to L of n, for example, right? So that is the set that you have. Moreover, when you want to define a relation and of course, again, if you want to a better explanation of what I'm saying right now, you can of course go over here and, for example, watch these videos that talks about the Cartesian product of sets and relations, and watch them in in order so that you understand the concept completely. But just as a brief explanation, I would say that basically once you have this set, then R is a relation defined on this set, meaning that you want to calculate the Cartesian product of this set with itself, meaning that you calculate the Cartesian product of L and L, and that gives you some set that contains all of these ordered pairs as, for example, L1, L2, L1, for example, L3. And of course, it's also possible to get L1, for example, L1. It's also possible to get L1, L2. It's possible to get L1, L3, and so on and so forth, all the way up to L1, L of n. Next, you will have basically, for example, something like L of n, L of 2, L of 1. Then you have L of 2, L of 2, for example. Then you have L of 2, L of 3, and all the way up to L of 2, L of n. And you can just keep going all the way up to basically L of n, L of 1, and you can just keep going in this direction until you get to L of n, L of n. Right? So that becomes the Cartesian product of these two sets. The Cartesian product of L and L. Now this set, of course, is a large set, and the relation is a subset of the Cartesian product of the two sets. So you can say that the relation is a subset of the Cartesian product of L and L based on some rule or condition. It's basically the same thing as saying that, for example, the set A is, for example, the set of, it's the same thing as saying that, for example, set A is the set of all the students in a university. The set of all the students in a university. That's a large set. So then you would have basically A is equal to, for example, student 1, you have a student 2, student 3, and I don't know how many students you have there, but there is a number for them, and that is basically the last student. Let's denote the last student with S of n. Now, in this case, basically the Cartesian product of A and A would be basically, if you imagine that you have this set over here, meaning that you have S of 1, S of 2, S of 3, all the way up to S of n, that is the set A. And again, if you have S of 1, S of 2, S of 3, all the way up to S of n, that is again the set A. Now the Cartesian product of the set of the set A and A is basically when you take all the possible members of A with all the possible members of A, meaning that S1 with S2, S1 with S1 with S1 with S1, S1 with S2, S1 with S3, all the way up to S of n. And then when you take S2 with S1, S2 with S2, S2 with S3, all the way up to S of n, and so on and so forth. So as you can see in this particular case, for example, the Cartesian product of A and A would be basically S1 with S1 and S1 with S2 and S1 with S3 all the way up to S of 1, comma S of n. And then you can just keep going all the way up to basically S of n, all the way up to here, S of n, comma S of 1, and S of n, comma S of 2, and all the way up to S of n, comma S of n. And that becomes the Cartesian product of these two sets. Now this set is a large set, right? Now I define some rule based on which some of the students of this group are going to be related to some of the students of this group, depending on that rule. For example, I'm going to say that R as a relation is equal to all the ordered pairs, for example, x comma y, such that, for example, I don't know, in a university what happens usually, for example, in such a way that, for example, x likes y. Meaning that if the first student likes the second student, then that ordered pair is going to belong to R, otherwise not, right? And based on that rule, let's suppose that, for example, S1 likes S1, for example. Then your R will be basically S1 comma S1, and S1 comma, let's suppose that S1 likes S2 as well. S1 comma S2, and let's say that S of 2 also likes S of 5, and that's the only basically relationships that there are. That's the only basically human relationships that there are in that university, meaning that one single person likes himself or herself and another person, and there is also another person that likes another person. So that is going to be the relation that you have, right? Now, based on this example, you can see that if I basically draw this, if I depict this using arrow diagram, I will have basically S1 and S2 in this set. I will have S1 and S2 in this set, and of course there are all of the other elements here, right? And so let me draw this properly. So I will have basically S1, S2, S3 all the way up to S of n, and this is set A, and also S1, S2, S3 all the way up to S of n. This is again set A, and what I'm saying here is that based on this relation, S1 is related to S1, S1 is related to S2, and S2 is related to S5, right? Now this is called a relation. This is called a relation, right? But the problem is that this relation The problem is that this relation, of course that's not a problem in any way, but that's just a fact that this relation is not a function. Now what is a function? Basically a function is a special type of a relation. Meaning that if you have such a relation, and if your relation has specific properties, then you can call it a function. Now, what is basically the rule what is basically the properties that have to be taken into consideration so that the relation becomes a function? So basically in a you know that in in a function, every member of a domain has one and only one image in the codomain. So what that means is that this first set over here, that basically you can call it the first set and you can call this the second set, for example. And this is called the domain because the elements are mapped from here to some other set, right? So this you can call the domain. Of course, talking very loosely, I mean using the word domain loosely in here, and this you can call the codomain. So basically every member of the domain has one and only one image in the codomain. So you can see that now each of these elements that you can see over here, since they have been mapped from the same element, S2 is an image of S1 under the relation R. Or you can say that S2 is an image of S1 under the relation R. And you can see that S3 is the image of nothing because it's not related to anything in this set. Moreover, S1 is called the pre-image of S1, for example, or S2 under R. Or S2 here is the pre-image of S5 under the relation R, right? Now, if a relation has to be a function, every member of the domain, which is basically to say every one of these elements, has to have one and only one image in the codomain. Meaning that, as you can see right now, this element here has two images, which is not acceptable as a function. It's acceptable as a relation, not acceptable as a function. Which means that basically if I had something like, for example, S1, S2, S3, S4, and S5, if I had these elements here, and if I had some other elements, some for example A1, A2, A3, A4, and A5 here, and if these were two sets A and B, and if in this set S1 was related to A1, S2 was related to A2, S3 was related to A3, S4 was related to A4, and S5 was related to A5. You can see that in this situation, basically every member of the domain has one and only one image in the codomain. So this has one and only one image. This one has one and only one image. This one has one and only one image, and so on and so forth. So this is of course a relation. This of course is a relation. It's a relation that also qualifies as a function, right? Now, there is one important thing here that you need to take into consideration, and that is, we said that this, let's suppose that, let me give you another two examples here. So let's say that you have A, B, C, and D, have this set over here, and let's say that you have basically, I don't know, E, F, G, and H, right? So in this case, let's call it set A and set B, and let's say that for example set A, basically, let's say that this element is related to these two elements, this element is related to this element, and this is just simply not there. So now in this case, as you can see, this element has two images in the codomain, so this is not a function. This is not a function. But you could have the situation where you have A, B, C, and D, and let's say that this is, for example, set A, and you have E, F, for example, G, and H, and this is, for example, set B, and let's say that this is mapped to this one, this is also mapped to this one, this is mapped to this one, and this is mapped to this one, right? So you see that this basically this element over here has one and only one image in the codomain. This element over here has one and only one image in the codomain. This has one and only one image and one and only one image, so this is a function. Now in this definition, we said that every member of the domain has one and only one image, meaning that basically in this situation, you saw that we said that this was a function. Now let's suppose that there is some element over here, for example I, for example, and this I is not related to anything. Since here we said that every member of the domain has to be related to some element in the codomain. Since this is not related to anything, then this is then not a function. This is then not a function, right? This has to be related to something, meaning that if, for example, if I relate to this one, then that is actually a function. So that is basically the whole story there. Now in this, so now you know what a relation is, you know what a function is, you know what the Cartesian product of two sets is, and you know basically essentially the whole story. Now let's go back to this example here. Okay, I think that's enough, but let me finish this thing. Okay, so now we said that basically here what we said was that let L be the set of all lines in a plane and R be the relation in R, defined as R is equal to all the ordered pairs L1, L2, such that L1 is perpendicular to L2. That means that basically you calculate the Cartesian product of L and L, you will get all of these ordered pairs. Now, based on this condition or rule, what it means is that in whichever one of these ordered pairs the two lines are perpendicular, then that ordered pair belongs to R. Otherwise it does not belong to R, right? Now, so that's basically the meaning of this relation. Now, you want to show that R is symmetric but neither reflexive nor transitive. Now, these conditions are simple. There is nothing very much complicated about these conditions. So let's go through them one by one. Okay, so now about basically what we wanted to do here, we wanted to basically show that R is symmetric, right? Now to show that R is symmetric, so what that means, basically what the definition of symmetry is in those relations, is that basically if basically we said that if A1, A2 belongs to R, then that implies that basically A2, A1 also belongs to R. That is the definition of, that is the condition for symmetry. Meaning that if you find, for example, some element like 2, 3 belonging to that relation, then that implies that basically 3, 2 also belongs to that relation. And then you can call that relation symmetric, right? Which means that now in this context, we said that basically R is all the ordered pairs L1, L2 such that L1 is perpendicular to L2, right? Now let's suppose that for example L1, L2 belongs to R. That means that basically L1 is perpendicular to L2. But if you have basically two perpendicular lines, and if this is L1 and this is L2, when I say that L1 is perpendicular to L2, that automatically implies that L2 is also perpendicular to L1, right? So then here you can say that means that L1 is perpendicular to L2, which implies that L2 is perpendicular to L1. Meaning that basically L2, L1 also belongs to R, right? So now here we have shown that if basically L1, L2 belongs to R, then L2, L1 also belongs to R. Therefore, R is symmetric. So here we are saying that if A1 comma A2 belongs to R, then A2 comma A1 also belongs to R, which is the case here. Now about the other two parts, we want to show that R is not reflexive. To show that R is not reflexive, what you can do is that, first of all, the definition for being reflexive is that, or the condition for being reflexive is that basically we said that for any A belonging to the set A, then A comma A has to belong to R, right? Meaning that, for example, if you have some set A, for example, that contains, for example, 1, 2, 3, 4, so you can see that here 2 belongs to A, right? So if 2 belongs to A, then 2 comma 2 also belongs to, and 2 comma 2 belongs to R, then that means that R is symmetric. Or for example, if 3 belongs to A, then 3 comma 3 belongs to R. That means that then basically R is symmetric, and so on and so forth. Now what that means in this context is that basically we are talking about basically all the lines in a plane, and then the rule that we have, basically our relation is that L1 and L1 comma L2 belongs to R. The rule that we have here is that basically all the ordered pairs L1 comma L2, R is basically all of these ordered pairs L1 comma L2, such that L1 is perpendicular to L2, right? So now here, let's suppose that, for example, let's suppose that L1 comma L2 belongs to R, right? That means that there are two lines where basically okay, so basically about being reflexive, well, we don't really need to consider this condition here. So of course you know that basically, of course, L1 comma L2 can belong to R if L1 is perpendicular to L2, which is not a problem that can be. There is no problem with that. But basically, L1 comma L1 cannot belong to basically R, since there is no line that can be, that is basically perpendicular to itself. That is perpendicular to itself, right? So there is no line that is perpendicular to itself, and so for any L1 belonging to the set L, therefore for any L1 belonging to the set L, L1 comma L1 does not belong to R, and therefore basically R is not reflexive, right? So that is about being reflexive. Now, in order to show that R is not transitive, here we want to show that it's neither reflexive nor transitive. Now, to show that R is not transitive, so the condition that we use for a relation to be transitive, we say that basically if basically a1 comma a2 belongs to R and a2 comma a3 belongs to R, if these two belong to R simultaneously, then a1 comma a3 also belongs to R for all basically a1, a2 and a3 belonging to A, right? So that's the condition that we use for transitivity, or for being transitive, which means that, now suppose that, for example, in the case of these lines, suppose that, for example, L1 comma L2 belongs to R. That means that L1 is perpendicular to L2, and also L2 comma L3 also belongs to R, meaning that L2 is perpendicular to L3, which means that basically that there would be some situation like this. Let's say that this is L1 and this is, for example, L2 and this is, for example, L3, right? So L1 is perpendicular to L2, L2 is perpendicular to L3. Now you can see that L1 and L3 are not perpendicular. L1 and L3 are parallel lines. So that so in this situation, if that is the case, then L1 comma L3 does not belong to R, because L1 and L3 are parallel lines, right? So and you can say that therefore the basically R is not transitive. So this is how you use, for example, how you use these concepts in a particular situation in order to say whether a relation is reflexive, transitive, or reflexive, transitive, or symmetric. So that is basically, that was example number 3. Now we have example number 4. We have example number 4 here, which is show that the relation R in the set 1, 2, 3 given by this relation is reflexive but neither symmetric nor transitive. So this is a good concrete example, and in the case of such concrete examples, you don't really have to think too abstractly. These are at least more helpful in the beginning when you're getting to know a concept. Most of the time it helps to consider some concrete examples, and then of course after that you can generalize the concept to more abstract ideas, or to more abstract concepts. So we want to show that the relation R in the set, want to show that basically the relation R in the set basically 1, 2 and 3 given by R is equal to 1, 1, 2, 2, 3, 3, 1, 2, 1, 2, and 2, 3 is reflexive, but neither is reflexive, but neither symmetric nor transitive. Neither symmetric nor transitive. So when you say that it is reflexive, what that means is that when basically the condition that we use for reflexive is as follows. Okay, so as the condition for being reflexive, we said that for any A belonging to the set A, then that the order per A comma A has to belong to R. If that is the case, then we say that R is reflexive. This is the condition. Now over here, as you can see, basically the set that we are talking about, or the set under study, the set on which the relation is defined, is basically a set containing 1, 2, and 3 elements. So that means that if, for example, 1 belongs to A, if I take this set as A, for example 1, 2, and 3, then you can see that 1 belongs to A here. Then that means that if R has to be reflexive, then that means that 1, 1 has to belong to R. And that means that R is reflexive. Basically, if, for example, if 2 belongs to A, then 2, 0 has to belong to R. And if 3 belongs to A, then 3, 3 belongs to R. If this is the case, then you can say that R is reflexive. And as you can see, 1, 1 is there, 2, 2 is there, 3, 3 is there. And so you can say that, of course, R is reflexive. You can say that basically R is reflexive. About showing that R is not symmetric. So for symmetry, what we use is that we say that so the condition for symmetry we say that basically if A1 comma A2 belongs to R, then that implies that basically A2 comma A1 also belongs to R. So if A1 comma A2 belongs to R, that implies that basically A2 comma A1 also belongs to R. And then we say that basically R is basically symmetric, right? This is the condition. Now over here you can see that basically 1, 1 belongs to R. So then 1, 1 is of course symmetric with 1, 1. There is no problem with that. 2, 2 is symmetric with 2, 2. 3, 3 is symmetric with 3, 3. 1, 2 is symmetric with 2, 1, which is not there. And 2, 3 is symmetric with 3, 2, which is not there. So as you can see, basically you can see that 1, 2 belongs to R, but 2, 1 does not belong to R. And that is enough to show that it's not symmetric. Therefore, basically R is not symmetric. The condition for transitivity of the relation R is that if basically A1 comma, for example, A2, and if this belongs to R, and also if A2 comma A3 belongs to R, that implies that basically A1 comma A3 belongs to R. That is the condition that we use for transitivity, which means that you can see over here 1 comma 1, and then you can see that over here 1 comma 1, and then basically 1 comma 2. So you can see that 1 comma 1 and 1 comma 2 belong to R, right? So 1 comma 1 belongs to R, and also 1 comma 2 belongs to R. And 1 comma 2 belongs to R. That means that, and this has to imply that 1 comma 2 belongs to R, which is the case. 1 comma 2 already belongs to R. And you have 1 comma, you have 1 comma 2, 2 comma 3. 1 comma 2 belongs to R, and 2 comma 3 belongs to R. That has to imply that 1 comma 3 belongs to R, which is not the case. 1 comma 3 does not belong to R, meaning that 1 comma 3 does not belong to R, and therefore you can say that R is not transitive. So let me take a look at this situation. So the solution that we have here is R is reflexive, since 1 comma 1, 2 comma 2, 3 comma 3 lie in R. Also R is not symmetric, as 1 comma 2 belongs to R, but 2 comma 1 does not belong to R. I don't know what, we use the same condition here. And similarly, R is not transitive, as 1 comma 2 belongs to R, and 2 comma 3 belongs to R, but 1 comma 3 does not belong to R. Okay, so very simple, but in order to understand basically in order to be able to solve these problems, it's very important to, first of all, to understand the concept. And well, the concept, you can, of course, I did try to explain the concept in this video, but of course that might not be enough. So if you feel that you don't really understand what you're doing here, you can go to basically you can go to this YouTube channel, search for this name. This is my own YouTube channel, and please go to the playlists, and if you look for NCERT Mathematics Class 12 Relations Functions, you will have access to all of these videos. And then over here, of course, it would take you around excuse me, it would take you around, like, for example, 2, 3, 4 hours at least to understand the concept here. But then that's I suppose the only way to do it. And that's it basically. Now let's do another example here. Let's do another example here. I'll end this video here and we will continue in the next video. Thank you.